Okay, so the next talk is fast AES-based universal hash functions and max, featuring LeMac and PetitMac. Augustin Barillon, Gilles Baudret, Gaëtan Roque, Claire Pernot, Léo Perret, and Thomas Perret, whatever. I'm sorry. And Augustin will give the talk.
Yes. Bonjour tout le monde. Thank you for the introduction, Bart. And I'll present, fast AES-based universal hash functions and max framework, and present two designs, LeMac and PetitMac. So as you all probably know, MACs are used to provide integrity and authenticity among an insecure channel. That is, if Alice wants to be sure that the message she receives comes from Bob, they pressure a secret key, and Bob, while sending the message, hard to derive if Eve doesn't know the secret key and wants to produce a fake tag. So there are several ways to produce such MACs. They can be built by several different cryptographic primitives, such as hash functions in HMAC, for example, block ciphers using encryption modes, variants of encryption modes, such as CBC-MAC, CMAC, or EMAC, and cryptographic permutations. If you see the sponge, the duplex mode or an ASCON mode as only associated data scheme, it produces a MAC from a permutation. But what we will be interested in this talk is MACs built from universal hash functions, which are some functions introduced by Carter and Wegman in 1977, and that have weaker security notions than standard cryptographic primitives, so that they can be more lightweight. They can, in particular, be proven with algebraic constructions, which is not the case for most cryptographic primitives. And usually we combine them with a few other components, such as block cipher calls, to produce a MACs. And such MACs are, for example, GMAC, Poly 1305, and UMAC. So in this work, we will try to exploit the fast AES instructions in modern processor to produce fast UHFs, and then we will convert them into MACs with generic constructions. So we propose a new generic framework from universal hash function and two new MAC designs, LeMac and PetitMac. So first, what is a universal hash function? It's some function that goes from, it's a family of functions indexed on a key K belonging to a key space from A to B, which have some security properties. And in our case, we will look at the case where the input set A is the set of messages of arbitrary length, and the output set B is a fixed size n-bit output. And the key K is K bits. So one main security notions in UHF is epsilon almost universality property, which is that when you take any two distinct message M and M prime, there should be only a fraction of the key space for which they collide. And actually, you can also write it like if you and actually this looks like a differential. And if we can ensure that there is no high probability differential from a non-zero message difference to a zero output, then we guarantee that it is epsilon almost universal. But of course, we can't do that, but we use heuristics. So what we do in this work is to use AES instructions inside the UHF. And we will use the design strategy of similar to the one of Roca, which is to have a round function based on AES with white states, and some message is incorporated at each round in it. And we will use assumptions, kind of standard assumptions in cryptography, which are that the best differentials in this universal hash function correspond to the best differential trails, and that the round are independent, so that we can look for the best differential trails with automated tools such as MILP. And once we have this UHF, we plug it into the encrypted Wegman-Carter with the Davis-Meyer construction presented in Crypto 2016 and produce a MAC with 2 additional block ciphers. And this MAC is non-spaced, and actually it's beyond birthday, without misuse. And we will instantiate the encryption E with AES. And what should be noted in this construction is that typically it's a fixed cost. So if we manage to optimize the performances of the universal hash function, we will have a fast MAC. So we will use AES instructions for that, and AES9 instructions, which were introduced by Intel in 2008, are composed of the 4 core operations of the AES round. That is to say, subbytes, shift rows, mix colon, and add key. And it should be noted here that the add key occurs at the end of the round. And so that this add key takes any key and corresponds to a free XOR. And this kind of AES instructions goes almost as fast as a standard XOR or add instruction, but it has much stronger cryptographic properties. So we try to exploit these cryptographic properties in our scheme. For this, we also need to define the rate, which is the number of AES instructions needed in our constructions per message processed, taken as 128-bit blocks. So a lot of MACs in the literature have low rates, such as rate 4, rate 3, and rate 2. And it should be noted that the most recent one, almost all achieve rate 2. That is to say, Jean Nicoli, Roca, and SMAC, which will be presented in the next talk. But in order to optimize fully the AES instructions, we need to dive into pipelining. So the AES instructions, we can launch several AES instructions per clock cycle, but there is this condition that the input of the AES instructions that we want to launch at the same time as the other AES instructions does not depend on the output of the other AES instruction. So if we ask for an AES instructions to the processor, we can only get the output 3 clock cycles later on some processors. And so we need to manage this pipelining by parallelizing at maximum the AES instructions in the pipelining. And actually, because most modern processors have a throughput of 2 AES per cycle, when we have a rate R constructions, we cannot get a better performance than R over 2 cycles per 128 bit of messages. And this actually is not a bound that is not achieved by recent MACs. Actually, because there is some dependency in the AES instructions, and the pipelining cannot be fully achieved. So that's our objective, to have a rate 2 constructions with optimal, almost optimal parallelization, and achieve this 0.0625 cycles per byte performance. So what we did is build a very general framework with a lot of parameters. Each wire in the figure corresponds to a 128-bit value. There are 2 main parts in our construction. The right part is the message schedule. It's totally linear. It takes as input some messages blocks at each round and has extra memory registers and is updated with a linear matrix, which will be chosen sparse. It is to be noted that at each time, the memory registers contain linear combinations of the messages so that they can be easily modeled in MILP. And on the left part, you have the main states, which is designed similar to SPN cipher, but where the linear part is sparse, so the matrix L is sparse, and the S-box layer is just composed of AES rounds. So AES1 is one round. To be noted that in the general constructions, we also allow some wires to be identity. The XOR of the output of this message schedule goes to the states and is included into the AES9 instruction with the free XOR in the free add key operation of the AES9 instruction. And in this framework, we have a lot of candidates and we need to filter them out. So what we do is just sample random candidates and then check their security and their performance by analyzing the best differential trails that lead to collision. And if there is no good differential trail that leads to collision, probably it is epsilon almost universal. And we also check the performance on the fly, which was not done automatically before our work, which is we generate the C implementation of the candidates and we ask the compiler to optimize. So this led to some nice candidates, and in particular, this universal hash function that is used in LeMax design. So as you can see, there are 4 wires in the message schedule part and 8 AES per round out of 9 wires in the main state. And every round we add 4 messages. So it's RAID 2. And it has a nice parallelization so that we reach the performances close to the theoretical bound. Actually, in the original version of the paper in Tusk, we showed this candidate and we claimed that it has at least 26 active S boxes in any differential trail, but there was a mistake. The only difference is in the message schedule part where we misrepresented our candidate here. So this one has at least 25 active S boxes by luck, I would say. So it is still probably secure. We renamed it LeMax 0, but and it will be a nice target for cryptanalysis before LeMax maybe. We also designed Petit Mac, which is a small variant where a message is added every other round. And it has only one AES wire, so that maybe it can be good for microcontrollers or hardware. All in all, we looked for a lot of different parameters, and we found the first candidate, a secure candidate with rate less than 2. But it doesn't have the same performance. It has a worse performance than our LeMax candidate because of pipelining issues, or because the number of XOR inside starts to account for a considerable performance loss. To be noted here that the first one corresponds to LeMax universal hash function, and the last one to Petit Max universal hash function. So as a performance results, so LeMax, we can see that on modern processors, Intel Ice Lake and AMD Zen 3, it has the best performance among existing Macs. So LeMax is mostly done for software performances. And Petit Mac was designed not to compete with the best Macs on software, but maybe more for microcontrollers or hardware. So in conclusion, we showed it's less than 2 candidates. And we showed the 2 new Mac designs, LeMac and Petit Mac. Now there are still some open questions that could be answered in future works. We could use AVX 256 or AVX 512 instructions for further speed up. And we could also design some similar framework, not for Intel instructions, AES9 instructions, but for our ARM instructions, which differ slightly because the add key is not after the round, but before the round. And eventually we could also do an AEAD, similar to Roca. Thank you.
Okay, thank you. There's already a question in the back.
Thank you for the talk. Can you explain the matter? What is automatic benchmark?
So once we have our candidates, so let's say I will take an example, the Mac. We have our candidates, and then we test its security. We see that it has a nice security. Then what we can do is create some variables in C, for example, exactly ask for this encryption. So we ask for the encryption of the round function, then we enroll it a lot of times, and then we ask for the compiler to just compile the assembly instructions, and then we measure the time it takes to process, let's say, 16 kilobytes message. And if it's too long, we just assume that the dependency between the IES rounds is bad and that the pipelining cannot be fully exploited. And so that probably it's not, well, we just discard the candidate and hope for a new, more performant one.
Okay, any other question?
Yeah, I think.
Yeah, so just 1 minute. So the automation is coming from the compiler, right?
Yes,
Okay.
because it's not easy to do by hand. And actually the compiler, it's the work that he already does. Like a lot of people have tried a lot of time to optimize the assembly instructions inside, like how the compiler works. So we reuse the work from the compiler designers, and we don't have to check the dependency by hand.
Okay. Thank you.
Yes. Yeah, sure.
Very nice work. Do you have an idea what the performance is on the ARM? Because it kind of doesn't make sense to make a scheme for every processor, right? In practice, especially for communication settings, the sender can have an Intel and the receiver can have an ARM, and you won't have a kind of good compromise between both.
So so we didn't benchmark on IRM. However, the IDE key, so there is, after each AES instructions on Intel, there is a free XOR. So here, as you can see, the M7, this XOR is included into this AES, and it's free. So it's included into the AES9 instruction. But on IRM, it's not, that key is not after the AES round, but before. So then we would need, for example, for LUMAC to include in this IES, include this XOR, this message XOR. So I think that for LUMAC, it should still be possible to have some nice optimization. But for the general framework, we only ask for the XORs to be XORed after the AES round. So probably we should either only keep candidates that could be performant for both cases, or redesign another framework, or try to optimize LUMAC, as there are some things to be done.
Any other question? So I had two questions. First, a silly one. Suppose the message is 4 blocks. How does this picture look like then? I mean, that there's a round function, so there should be multiple rounds.
So actually, so the goal is to here the message 1, for example, will be non-zero and will still be here.
Yes.
So we will still iterate it a few
But
times.
if the message is 4 blocks only.
Yeah, 4 blocks, we would still iterate with empty messages until the left part is empty.
But is it then not more than rate 2? You said rate 2, so that's 2 AES rounds.
Okay, yeah.
So that's
asymptotic. Rate is an asymptotic value.
Yeah, okay. So one other question, if you look to other schemes like AZ or whatever, they use round-reduced AES. They don't dare to claim security beyond 113, for instance.
Who?
AZ, for instance. And what is your claim security level here then?
It's probably around 128 bit, but maybe there are few security loss. I think we claimed 128 bits still because it's hard to know which difference can like we know we don't have an epsilon almost universal function with epsilon equal to the minus 128, but it's hard to produce such a differential.
Okay, any other question? If not, then let's thank the speaker again.